Good afternoon, everyone. We'll get started here in just a minute. All right, good afternoon. Thank you for joining us today. I'm going to go ahead and get started. As we go through today, if you have any questions, do send them in using the question and answer or chat part of the Zoom interface. Either one works for me. And depending on the question, I'll either answer it then or I will hold off until later. So today we're talking about our Wi-Fi 101 presentation. It's been a few months since I've done one of these. And the idea behind it isn't to talk about really our products that much. There'll be a little bit of that, but not a lot. It's mostly just sort of talking about Wi-Fi and how it works. I find in this day and age, there's still a lot of people out there that don't really understand how it works, which often leads to problems with deployments out in the field, not understanding, how many APs you can cram into a certain area, or understanding why it is that the signal works in bedroom one but doesn't work in bedroom two, things like that. And it really helps to have some background if you are deploying Wi-Fi networks to really understand what you're dealing with. So just to start, for those of you that are new, we'll just do a quick slide here on the backgrounds of Zycell. And this slide's a little bit out of date. We've been making computer networking equipments since 1989. I have been with Zycell since 2003. We are a global company. In fact, the US is one of our smaller markets. Um, but we have 150 different global or markets we use out there. We've deployed over 1 million devices out in the field. And today, since we're talking about Wi-Fi, I should mention that we've been doing Wi-Fi since the very earliest days of Wi-Fi. Back when it was just called 802.11. When I joined the company in 2003, we still had some of that equipment sitting in our RMA pile in the warehouse. So with that, we'll go ahead and get started here. So we'll start taking a look here at the timeline. So Wi-Fi has been around since 1997. That's when the original 802.11 spec was ratified. I'm guessing there was probably some hardware a little bit before that. Um, so Wi-Fi has been around for a long time, and the core fundamentals of Wi-Fi are the same today as they were back then. Um, as far as the technology goes, Wi-Fi 6 and Wi-Fi 7 were the first really significant changes to how Wi-Fi operates, or at least giving some flexibility in how Wi-Fi operates. So a lot of those issues that we had with Wi-Fi back in 1997 are still the same issues we were dealing with 11AC, and somewhat to do with Wi-Fi 6. And some of that stuff is still sticking around even with Wi-Fi 7. I mean, there's only so much we can do with the physical propagation of radio waves and stuff like that. Now, these timelines on here are kind of fuzzy. So we'll use Wi-Fi 7 there down at the bottom as an example. Um, you'll see there the date is 2024 is the ratification of Wi-Fi 7. But as you know, there have been products on the market claiming to be Wi-Fi 7 for at least 2 years before that, maybe even a little bit longer on the consumer space. And if you go today to the IEEE website, you will see that I 802.11be, aka Wi-Fi 7, is still an in-progress standard. So even then, this drags on and on and on. And if everyone waited for the certification or the standard to be ratified and finalized and published, we would never, we'd still be using the 802.11 AC stuff from back in the day. Um, so I bring that up because things are confusing. Things can overlap, and what happens is when people rush stuff out before the standard is fleshed out enough, you may end up in situations where the chipsets that claim to be a certain level of Wi-Fi are actually missing certain features that are part of the standards. Even 802.11be is expected to have a phase 2 implementation. So IEEE is who makes the standard. So they're the ones who create these standards. 802.11 is the part of the standards, and they make standards for all sorts of types of stuff. So they create the official standard. One of the problems we ran into in the early days of Wi-Fi is obviously with these standards, there's no enforcement mechanism, so you didn't have to follow the standard, and it's something that's written by a committee, and there's always different ways to interpret certain things. Otherwise, right, we wouldn't need lawyers when it comes to legal stuff because these spend months pounding out a bill and negotiating on the right terminology, and then a few years down the road, people interpret it differently than intended, and you get to argue about it. Same thing when it comes to IEEE. So the manufacturers and sellers of Wi-Fi products decided they needed to do something about it to make sure everybody's products worked with everyone else's, and that there were some guarantees as to what technologies the product would have. And that's when the Wi-Fi Alliance got formed. So that's sort of what they do. IEEE makes the initial standard. The Wi-Fi Alliance sets up a series of tests to ensure interoperability. And they also, help clarify things. So if there's some confusion or disagreement on how to implement part of the standard, Wi-Fi Alliance helps with that. And they also will tell you what parts of the 802.11 EEE standard you need to actually comply with. So, right, with any of these Wi-Fi standards, there's a lot of optional components or questions on what's optional and what's required. And Wi-Fi Alliance steps in on that. So they're the ones who created and trademarked the name Wi-Fi. And when you see the Wi-Fi logo on products, that's why. They're also the ones who decided a few years ago to rename Wi-Fi technologies from 11B, 11AC, etc., to Wi-Fi 5, Wi-Fi 6, Wi-Fi 7, thinking that would be a lot easier for consumers to be able to understand. Now, you don't have to get your products Wi-Fi certified. In fact, a lot of enterprise and business class products these days don't bother with it, but they are still a big factor in things. Another, just to add to the confusion here, is the standard for Wi-Fi 7 certification today is different than the standard for Wi-Fi certification a year ago. As the chips progress, as the quality of code progresses on the standard, they are modifying things. So a product that you bought a year ago that was Wi-Fi certified may be missing features that are required today for that same certification. And then lastly, there's the FCC, the US federal government. They control the radio waves that Wi-Fi uses. They determine what frequencies we can use, what powers we can use, and as well as other aspects like bleed over and things like that. So these set up the rules. Now, the FCC isn't that great on enforcement. There have been situations specifically dealing in the Wi-Fi industry where competitors have had to sue each other because one competitor was violating the FCC rules and the FCC never got bothered to do anything about it. But there are rules for this, and in order to be able to ship a product, we have to be certified that we are meeting the rules. We pay for that ourselves, and we use a third-party processor to do that. So basically, to get a product FCC certified, you go to a certified lab, you pay them money, they test it, and then they publish the report to the FCC saying that you are in compliance or not. In theory, the FCC should be checking products when they get imported and doing spot checks, but in reality, they don't really do that. So I'm going to bring up, this is an old slide I used to use, and this is just sort of as an example when it comes to, Wi-Fi technology. So in this case, it was when is Wi-Fi 6 really isn't Wi-Fi 6. And so what happened is the early draft of the IEEE spec was out, and chipset vendors rushed to be able to make products that they claimed were Wi-Fi 6 compatible. And a lot of those first gen chips on here, I'm using Qualcomm, but this is true of the other chipset vendors as well. This is just one where I had all the spec details. But the Gen 1 Wi-Fi 6 chips were missing some very important features that were in the in the Wi-Fi 6 Gen 2 chips. Um, so this is what I'm talking about, some of the differences here. The ability to do upstream OFDMA was not part of those first gen chips, and it was not something that could be added with software. Same with doing upstream MIMO. Couldn't be done on those first gen chips. So by rushing and being one of the first to market, you ended up missing out on some very important features. And these are features that really differentiated Wi-Fi 6 from Wi-Fi 5 that came before it. Another thing that happened here in the Wi-Fi 6 days was a certain vendor was advertising and selling a Wi-Fi 6 product. Now, previous to Wi-Fi 6, we had 11AC, Wi-Fi 5, and that was only on the 5 gigahertz radio. There were no changes to 2.4. So with an 11AC product, your 2.4 radio was still 11N. With Wi-Fi 6, that was an improvement to both the 2.4 and the 5 gigahertz radios. So this one other hardware vendor was selling their Wi-Fi 6 products, but they only put Wi-Fi 6 on the 5 gigahertz radio. If you check the data sheet, you would find that the 2.4 radio was still using Wi-Fi 4 technology for that 2.4 radio. So it isn't something that's going to be called out. So if you weren't, looking over the details on the data sheet, you might miss that your Wi-Fi 6 access point was only Wi-Fi 6 on one of the radios instead of both. Okay, so let's move on from there. Let's talk a little bit here about radio waves. So radio waves are what Wi-Fi uses to communicate. So both your client device and your access point or router are both transmitters. They transmit and receive radio waves that they are being sent to each other. And radio waves are radio waves. They behave the same way regardless of the frequency that you're using. So things that affect Wi-Fi are the same things that are going to, interfere with the behavior of your car radio, walkie-talkies, satellite connections, basically anything that's using radio waves. So some general rules here. As frequency goes up, it's generally easier to put more data into those radio waves as far as the encoding goes. So that's why, at least initially, 802.11a was faster than 802.11b. Obviously, as time goes on, there's ways to improve the encoding. Encoding technologies get better, allowing us to increase the speeds on those lower frequencies. And as frequency goes up, the range goes down. So as frequency goes up, the signal itself degrades faster. So a 2.4 gigahertz signal will travel farther than a 5 gigahertz signal, and a 5 gigahertz signal will travel farther than a 6 gigahertz signal. And that's true whether we're talking about open air or whether we're talking about going through obstructions like walls or trees or people. So again, as I was mentioning earlier, radio frequencies are regulated by the FCC, and most transmitters, you have to have a license to be able to transmit radio waves. And what they have done over the years is they've carved out various chunks of RF frequency that anybody can broadcast on as long as they follow the rules as far as power output and things like that. So initially, we had a little chunk here of 26 megahertz of spectrum that was available in the 900 megahertz technology. Then they opened up 2.4, then they opened up 5, and now today they've opened up 6 gigahertz. So as new technologies have come, in general, they've gotten wider, allowing us to use more bandwidth, but the frequencies have gone up, so you can cram more data on there, but the range is less. So if you're old like me and remember the days of household cordless phones, you might remember how this progressed. How it used to be your cordless phone sound quality wasn't that good, but the range was insane. You could hold a conversation with your friend and walk across the street to another friend's house while still maintaining that call. And as time went on, we jumped up here in I think it was the early 80s to 2.4 gigahertz. So improvement in the sound quality, but the range went down. You can no longer walk across the street to your friend's house. You may not even be able to use it in parts of your yard. And then in the early 90s, there was a big switch to 5 gigahertz. So the benefits of that again were better sound quality. But now if you have a big McMansion, you might not be able to get coverage in your entire house while you're talking to somebody. And these are the same radio frequencies that Wi-Fi is using because these are shared by everything, whether it's Wi-Fi, remote control cars, cameras, anything that's using wireless technology in general is using one of these chunks of spectrum. Now, the other benefit, as I mentioned before, is the bandwidth went up. So there's generally more bandwidth available. That means there's more channels that can be used that don't interfere or overlap with somebody else. And that's really important to keep in mind when it comes to radio transmissions as a general rule. We'll talk a little bit about some new technologies that give us a little bit of exception to this later on. But in general, only one device can broadcast at a time. If two or more devices broadcast at the same time, they interfere with each other and it turns into a garbled mess. If you've ever taken a road trip, you've probably encountered this when you're driving between two major cities and you get to a point where your radio is picking up, you know, 100.3 FM being broadcast out of Santa Monica, but it's also picking up, 100.5 FM being broadcast out of Hemet or wherever, some other city farther on, and you're picking up both frequencies or both stations at the same time, and the frequencies are either the same or close enough that they bleed over into each other, and it turns into an unlistenable mess. If you've ever worked with, those old analog walkie-talkies, same thing. If you had two or more people talking at the same time, it turns into a garbled mess. It's the same thing with Wi-Fi. So as I mentioned before, there's a limit on the range of your radio signals. Basically, as they travel over time, they do degrade. So one of the things we look at here is how to measure the strength of those radio transmissions. So on consumer products, traditionally you would see it rated in milliwatts, whereas on data sheets and on business class products, you usually see it as dBm. So these are both ways of measuring the same thing. So dBm is generally what you use, decibel milliwatts. I believe it's logarithmic or something similar to a logarithmic measurement. So for every 3 dB gain you get, so if going from 20 to 23, for instance, you're doubling the output power. So that's why consumer products switched over to using milliwatts, was because it seems like a huge difference between a 200 milliwatt radio and a 100 milliwatt radio. Whereas if you're using dBm, there doesn't seem like there's much difference between 23 or 20. Now, neither of these are particularly good at measuring the differences you would get in range, but I would say the dBm is a little bit closer. Now, one of the benefits of dBm is it can be combined with dBi, gain of your antennas. So in the old days, when removable antennas were very common for Wi-Fi and people were cobbling together their own combinations of things, it makes it really easy to be able to calculate the EIRP or the total combined broadcast of what was coming out of your device, because you could take the dB coming out of your chip, add in the dBi gain of your amplifier, subtract out the losses caused by your cables and connectors, and then add in the gain of your antenna, and add those all together using dBm and dBi to create a single, easy to understand number, where you can't do that with milliwatt. So something that gets overlooked a lot, especially when it comes to troubleshooting poor wireless connections, is the signal to noise ratio. A lot of people are simply looking at the strength of the signal being sent or the strength of the signal being received that they're trying to hear without taking into account other sources of RF noise. So generally, the quality of your Wi-Fi connection is tied to the signal to noise ratio. So you're able to achieve faster speeds, less drop packets, the better your signal to noise ratio is. So when we're talking about noise here, we're talking about other things that are creating RF on the same channel you're using. So for instance, we'll just use a 2.4 gigahertz radio in your home's access point. Your microwave also uses 2.4 to cook food. So when that's on, it may be leaking some RF signal, which raises the noise floor and interferes with your signal. Your neighbor may have their own router that's using the same channel or a neighboring or overlapping channel. So that's another source of RF noise. Your Bluetooth headphones might be using an overlapping or neighboring channel, which bleeds over and causes noise. So what you want to look at is, the strength of the signal you're trying to hear versus everything else that's creating noise on that same frequency. And then attenuation is something, and that's basically just, a measurement of how much things are degrading. As a general rule, the denser a material, the faster the signal attenuates or degrades. So that's why a signal can travel really far in an open air environment, but doesn't necessarily penetrate walls that well, or can go through wood stucco walls okay, or wood walls okay, but if you have stucco walls on the outside of your house, it won't go through it because of the metal in the stucco walls as well as the density of the concrete covering there, or why your signal in an office building isn't wanting to go through the elevator shaft because the metal is dense and blocking the signal. So there's some general rules here for you as to different losses you can expect to see. So you can see here a traditional glass window is going to give you around 3 dB loss of signal, which will cut your effective range to 70%. So you've halved, right? 3 dB is a doubling or halving of the power. So you have the power of the signal going through, and it drops the range by 30%. A tinted window, because that usually uses some form of metal, can drop the signal up to 8 dBi. And as you see here, as we go through the rest, it's just, the denser it is, the thicker it is, the more loss you're going to experience. For those of you that want to calculate the range, this is the formula up here at the top of the screen. So as you can see, it's a logarithmic scale based on the frequency and the power output that will give you your overall range. So when we start thinking about, attenuation and signal to noise ratio, we have to combine all of those together to determine how much range you're going to get. Now, something that often gets overlooked is that Wi-Fi is two-way communication. Even if you're streaming a video from somewhere to your device is still having to send packets back upstream, acknowledging that it has received the packets okay, and it is okay to go ahead and send the next packets on that stream. And this is something that gets overlooked a lot. So, your access point is often going to be 500 milliwatts or greater broadcast power. So that signal can go really, really far. But your phone or your tablet or your other client device that you're using to communicate using Wi-Fi is going to have a much smaller output power. So in this case, we're using milliwatts, so 25 milliwatt, maybe 40 milliwatt on the high end. So that signal cannot get back as far. So that is going to be the lower powered device is essentially determining your range. So we often run into problems with this when people do a site survey, where they do a site survey using a beefy, industrial work laptop that's got pretty good output power, and they'll go around with that. But then the clients come on site and the clients are using their phones or they're using an embedded device or something like that, and they don't get good quality signal. And that's why, because when you were doing your site survey, you weren't matching the limitations of the client device. And the range isn't what you thought it was going to be because the actual client devices being used are lower power. So a way to think about this is just having a conversation, right? Conversations are two-way. I talk to you, you talk back to me. And if you're in an environment where you, for instance, can shout, but your friend has a cold and they're not able to speak as loudly, right? You have to get closer together to make sure that you can hear what they're saying. Same thing when it comes to Wi-Fi. Now, when it comes to radio waves, they behave surprisingly very similar to water waves. So, it helps when you're trying to visualize things to think of a pond and you throw a rock in the pond and then waves radiate out from where that rock hit the water. And it's similar to what happens with Wi-Fi, only instead of a rock, it's a transmitter, whether it's your AP or a client device. Um, and it's the radio waves are radiating out just like the water waves do when the rock hits the water. And you see a lot of the same behavior. Basically, the radio waves radiate out in roughly a circular pattern, depending on the type of antenna you're using. And they interact with the environment. So they will hit something and then it can reflect off of it. I'm sure you've probably seen this before where a wave hits, say, a support for a dock, and the wave is actually able to wrap around it. Same thing happens with radio waves. They can hit something and wrap around it. Now, something radio waves can do that water can't is they can pass through solid objects. There might be some signal degradation, but these still are able to go through. Or the wave can hit, odd shaped devices and break off into multiple smaller ones. And this is important because it helps explain what sort of things you're going to see in the RF environment, when you put your access point somewhere, what you can expect to see it do. But it also causes issues. So you start with one signal and it can take multiple different paths, right? So the signal going through the transmitter, through the wall to your receiver is going to be physically shorter distance. So the signal will get there quicker. But then radio waves going out this way, hitting a wall and reflecting off of it will also hit the receiver. But because the path is longer, they'll be showing up slightly later, creating what would essentially be in audio terms an echo. So you get some weird echoes and distortion effects based on the RF environment, which is something that's hard to visualize and see, obviously, because radio waves are invisible and you're probably only looking at, the signal strength meter on your device to know how good the signal is. And it can't tell you what other stuff is going on. Now, another problem we have with Wi-Fi, as I mentioned earlier, is only one device can broadcast at a time. And so the way Wi-Fi solved this, going all the way back to the 90s, was a pretty simple procedure. And that is, if you want to send data, you sense the medium. What does that mean? It means you stop for, a microsecond or two and you listen to see if anybody else is broadcasting. If somebody else is broadcasting, you can hear them broadcasting, you then back off a random period of time and start the process over again until there's a time when you don't hear anybody else broadcasting. If nobody else is broadcasting, you go ahead and broadcast. So this leads to some of the problems we run into in denser environments. Basically, anywhere where as you increase the number of users or increase the number of active users, you start running into these issues. And what happens is 2 or more devices will be queued up waiting to broadcast. They will check the medium at the same time. Both will see no one else is broadcasting. So both will decide to go ahead and transmit. And as I mentioned before, that causes interference with each other and you end up in a collision situation. So that's why you get a lot of like drop packets and latency delays as you wait to rebroadcast until only you are the one broadcasting. Wi-Fi 7 has added some technologies to help reduce this, but this is still the default behavior for compatibility reasons on all flavors of Wi-Fi. So you can quickly imagine how this runs into issues when you are dealing with 30 or more client devices on the same access point. The other problem we run into is called the hidden node problem. And this is a huge issue for those of you that are WISPs trying to set up an outdoor WISP point-to-multipoint environment. Because in a point-to-multipoint outdoor WISP environment, you're using directional antennas, which amplify what we're about to talk about here, which is the hidden node problem. So again, if you remember that past slide, you wait and listen before you broadcast to make sure nobody else is broadcasting. In this scenario, we've got an access point in the middle of the room. You have one client device on the left side of the room, one client device on the right side of the room. Both are within range of the access point. They are able to see what the access point is broadcasting, and the access point is able to pick up the signal that they're broadcasting. But the hidden node problem has to do with when you sense that environment, these 2 devices are too far away from each other to be able to hear the other one. So this device has no idea that this device is already broadcasting. It thinks that there's no one broadcasting, so it chooses to send the data. And the signal from both of these arrives at the same time at your access point, causing interference at the access point level and causing packets to get dropped. So again, you can see in an environment, as you add more users, you increase the risks of the hidden node problem. And in the case of a WISP, where you're using a directional antenna to shoot the signal back to the base station, it's going to be a huge issue because that is only able to see the access point or the base station. It's not able to see all the other client devices. So the next topic I wanted to talk about here is data rate through throughput. So there's basically a bunch of different terms that describe how fast a device is and what sort of speed you're going to run into. And at any point, you can go to Amazon, pull up any wireless product that's got a good number of reviews, and you will see a lot of complaints that the device is advertised at one speed, but their speed testing shows that it's significantly slower. So again, there's a lot of different terms talking about speed. I think what I find to be a common way to think about it or look at it is the differences between data rate, which is what you will usually see speeds notated as on a data sheet, versus throughput, with throughput being what you measure using something like Ookla or speedtest.net or whatever other FTP file transfer, whatever you're using to approximate and test the speed of your network. So data rate is how fast the connection is between your client device and your access point. It's the negotiated wireless speed, and it includes all data that's being sent. Throughput for this terminology here for this slide is going to be what you speeds you see when you run a speed test. And when it comes to Wi-Fi, data rate is often twice or more faster than the throughput you're going to be able to measure. So why is that? And that has to do with overhead, protocol overhead. So when we look at Ethernet, a wired connection, there's very little overhead. Almost everything that you're being sent is taking up all of the bandwidth that's available. When we're dealing with Wi-Fi, we are dealing with Wi-Fi radio waves in an unlicensed chunk of spectrum where you have to play friendly with every other device that's also using that same chunk of spectrum. And you're transmitting this through a very lossy environment with all sorts of environmental factors which can cause issues. Not a problem with Ethernet. So because of that, the differences between data rate and throughput with something like Ethernet is like 3% or something very, very small like that. Where with Wi-Fi, there is a ton of protocol overhead and retransmissions and other things going on that you don't see, which eat up a lot of the data rate. So if you were to just measure what's coming out of the Wi-Fi port on your device, it's going to be a lot more data than what your speedtest.net transfer or your FTP transfer is, because your Wi-Fi device and the Wi-Fi protocols are adding extra data on top of that to verify that the data's gone through, it wasn't corrupted during transmission, whether or not it needs to be retransmitted, etc. So because of that, normally what you're going to see is a difference of at least 50% on Wi-Fi between the advertised data rate and the throughput that you can see when you do a speed test. And then on top of that, there's other issues, right, that may be causing things. There may be environmental issues that are keep preventing you from connecting at the fastest speed. It may be your client device is slower than what your access point is, right? So it may not be able to max out your access point. You may have to use multiple clients at the same time and add their data rates or add their throughputs together to get the overall rate. It may be that your router or your broadband connection is choking the speed test, all sorts of things like that. But the big one that people overlook is this data rate versus throughput. So data sheets and all materials that you see, regardless of who the manufacturer is, are going to be talking about the data rate, regardless of which terms they use versus throughput, which is what you're going to see when you do your testing. So one of the questions that comes up a lot is how do we get faster speeds? Why is it Wi-Fi 6 is faster than Wi-Fi 5 versus Wi-Fi 4, etc. So this is not how do you increase speed yourself in your home or in your customer's network. This is from a technology standpoint, how do we make Wi-Fi faster? So there's three primary ways that this is done. The first one has to do with encoding. How much data are we cramming into these data or into these radio waves? So as technology has gone on, we've increased what we call the QAM. So we've got 64-bit QAM, 256-bit QAM, etc. This is the encoding methodology that we're using. And that allows us to cram more data into the same exact amount of bandwidth on those radio waves. So you can see here 11N was 64 QAM. We went up to 256-bit QAM with 11AC. Wi-Fi 6 was 1024-bit QAM, and we now have 4096-bit QAM when it comes to Wi-Fi 7. The other thing we have is these things called spatial streams, and we will talk about these more later. But as a general rule, the more spatial streams you have, the more data that you're able to send simultaneously. And then the other one is increasing the channel bandwidth. How big is that channel that you're broadcasting on? 11G only gave us 20 megahertz channels. 11N gave us 40 megahertz channels. 11AC, wave 1 gave us 80 megahertz channels. Wave 2 gave us 160 megahertz channels. And with Wi-Fi 7, we have up to 320 megahertz channels. So we're using much wider channels, broadcasting more data. So let's start by going through that list backwards, and let's talk about bandwidth. So in the US, the 2.4 gigahertz spectrum that we use has approximately 60 megahertz of frequency that we can all use. And everybody has to share that same 60 megahertz. Now, the challenge we run into, though, is if you pull up, your router configuration, you will see 11 channels that you can choose from. The problem is those channels are actually 20 megahertz in width, but the spacing between the channels is only, I think, 5 megahertz between each channel. So what that means is you don't have 11 channels to choose from without overlapping. You realistically have 3 non-overlapping 20 megahertz channels. Anything that's not 1, 6, or 11 is going to be overlapping with 1, 6, or 11. And when you have that overlap, you're creating interference with the other users. So with 11N, we added 40 megahertz channels to 2.4. But again, we've only got 60 megahertz to play with. So because of that, if you're trying to use 40 megahertz channels, you can have one access point in the area, and that is it. Any second access point is going to be overlapping with your access point and causing interference issues. So 40 megahertz channels outside of, large lot single family homes, you're going to have interference issues if you try to use 40 megahertz channels. And in fact, most 40 megahertz implementations automatically drop down to 20 when they start seeing interference and rarely operate at 40, even if you set them to 40 for that reason. So the solution to this was the move to 5 gigahertz. Now, it took a while to do because 5 gigahertz doesn't travel as far, and people used to be really focused on range, so you can minimize the number of access points. But 2.4 became unusable for a lot of deployments for a lot of applications, so we moved to 5 gigahertz. So you can see here, each of these little triangles is a 20 megahertz channel. I think there's 26. So you've got 26 non-overlapping 20 megahertz channels versus 3 for 2.4. So it makes a lot of sense, especially in apartment buildings, condos, office buildings, where you've got a lot of access points and a lot of users, to move to 5 gigahertz to solve those interference issues and the lack of bandwidth that's available. Now you will notice we've got some areas of different color here on the chart. So this orange area is what we call DFS channels. So the problem we ran into is 5 gigahertz used to be licensed spectrum. It used to be if you wanted to use 5 gigahertz, you had to have a license to use it. So when they opened this up for unlicensed use, the problem you ran into is there's still users who are licensed users who are already using these channels. So the FCC said basically to use these middle channels, you have to use something called, digital frequency selection. Basically, if you're an unlicensed user, you cannot use a channel if there is a licensed user using that channel. So your job is if you detect a licensed user, you have to stop using that channel and find another channel, verify no licensed user is currently using that channel, and then you can resume broadcasting. So the challenge we run into here is there may be other licensed users in your area that periodically are using your spectrum. The other issue you run into is there may be sources of just RF interference from industrial appliances, from other devices that you're using that may be mistaken as a legacy licensed user. And either way, what happens is your users get dropped off the network, and there's a period of time for it to find a new channel and start rebroadcasting again. So for this reason, a lot of business users don't want to use DFS channels because it causes connectivity issues can cause connectivity issues for some of your users. The other challenge we run into is in order to get DFS certification, the certification process is longer and more expensive. So a lot of consumer products don't support these DFS channels. So it's a very common call that we get is, hey, we've deployed your access points and your access points aren't compatible with Bob's laptop. He can't connect. We've got 6 access points and he can only connect to one of them. Fix it. And what happens is we log in and check to see what they're doing, and we find that 5 of their 6 access points are using DFS channels, and Bob's laptop doesn't support it, which is why he can only connect to one access point. So for those two reasons, a lot of users are going to choose to not use these DFS channels, right? So that drops us from 26 20 megahertz channels that can be used down to 8 or 9 non-overlapping 20 megahertz channels. So it's a significant reduction. But also keep in mind, we want faster speeds. So to do that, we increase the bandwidth that we're using. So if we go up to 40 megahertz channels, we've now only got 4 non-overlapping 40 megahertz non-DFS channels that we can use. So we're almost as bad, we're just only a little bit better than 2.4 now on 5 gigahertz. And then again, as I talked about, newer technologies use 80 megahertz channels or 160 megahertz channels. So this is a common problem we run into. Again, consumer products can't use a lot of consumer products can't use DFS channels. So oftentimes there's no reason to even set your device to use a 160 megahertz channel because that has to overlap with DFS, and some of your client devices won't be able to connect to it. So you end up using only an 80 megahertz channel. So now keep in mind what we were talking about earlier with throughput versus data rate. Well, if you drop from 100, data rate on the data sheet is going to be at the maximum channel width that you could use. So in reality, though, you're only able to use an 80 megahertz channel. And because of that, your throughput's going to be halved right there just because you're not using the full potential of your radio because it isn't compatible with your client devices. So moving on from there, we'll talk about spatial streams. So you remember from my previous slides back there, I was talking about how radio waves can bounce off of things and wrap around things. And it creates this sort of echo effect where the signal, the same broadcast, is reaching your receiver multiple times, slightly offset, creating this sort of echo. So that's what we call multipath. And that was a huge problem until 11AC. With 11AC, some smart people, much smarter than me, found out that you can use this multipath, and instead of being a problem and trying to figure out how to filter out these horrible echoes, we can use these echoes to send different data simultaneously on different paths. So it takes advantage of the fact that on your access point, even if you can't see your antennas are physically located some distance apart from each other. And because they are located slightly apart from each other, the signals that they send will take slightly different paths in the RF environment. And so now what happens is, for each antenna that you have that's capable of broadcasting, you can send a different set of data and then combine them together on the client side for faster speeds. So in this case here, I think it's 11N technology, maxes out at 150 megabits per second. But if you had a second antenna broadcasting simultaneously using the same RF frequency, it'll take a slightly different path and you can send a different 150 megabits of signal. So that's how we get N300, was an N300 device is capable of broadcasting on two different antennas, two different data streams. And as long as your client device can hear and pick up those two different data streams, because it also has two different sets of antennas physically located slightly apart from each other, it can combine that together to get 300 megabits total data rate. If we had a third antenna that could broadcast, we would have a 450 megabit combined data rate. Now, there was another technology that we have, which is called multi-user MIMO, which builds upon regular MIMO. And what that does is it allows us to simultaneously broadcast two different streams or more, two or more streams, and target each of those streams to a different user. So the aggregated throughput is 300 megabits per second, but one client device is able to get 150 megabits, and a second client device is also able to get 150 megabit per second data stream. If you added a third antenna that's broadcasting, one could get 300 megabits and one could get 150, or however you wanted to split that up, possibly three clients simultaneously receiving data at 150 megabits per second. And then with Wi-Fi 7, we've allowed the ability for clients to be able to broadcast at the same time on the same channel and not interfere with each other by using these different spatial streams. So when you're looking at data sheets, especially Zycel data sheets, rather than use, N300 or whatever on business class products, you will usually see the spatial streams defined, 2 by 2, 3 by 3, etc. So what does that mean? That's telling you how many spatial streams you can send and receive. The first number is how many you can send. The second number is how many you can receive. So when it comes to access points and routers, first number and second number almost always match. If you can broadcast two streams, you can receive two streams. If you can broadcast three streams, you can receive three streams. Where you run into areas where these numbers don't match is when you look at the client devices. It's very normal to see a 2 by 1 or 3 by 1 on the data sheet for the Wi-Fi chip that's in your phone or your tablet. Basically, your phone or tablet is able to receive at a faster speed than it can transmit back to the access point. So it can receive two or three spatial streams and combine them together. But when it uploads data back to the access point, it can only send one stream. So that's where you will see those differences. Now, something you will see primarily on Cisco data sheets, but you will now see it on some of our data sheets, is you will see a big number followed by a smaller number after a colon. So what is that? 4 by 4 colon 3. That's telling you you have four antennas that can transmit, four antennas that can receive, but that the chip can only handle three of those at a time. So I hope that makes sense. You've got four you can use, but you can only use three at once. Right? You may have three forks on your table, but you've only got two hands. So you can only use two of those forks. You can use any two of those three, but you can only grab and use two of those forks at the same time. It's what's going on here. So what's the benefit of that? In theory, it gives you some options so you can change which antennas you were using dynamically based on the RF environment. To be able to choose if you had a 4 by 4 like by 3, like in this example here, that you can choose the best three antennas based on the current environment. So if the environment changes, maybe the best three change, and you can automatically change. So it helps you out a little bit. It's not a huge difference. So putting it all together, the speed is going to be determined by the bandwidth of the channel you're using, how many spatial streams you're using, and the QAM or the encoding that's being done at that time. So to figure out your maximum data rate, you combine these three together, and that tells you how much speed you're going to be able to get, right? So we'll just keep it easy. One spatial stream, 160 megahertz channel, 256-bit QAM, gets you 866 megabits per second. Now, as I mentioned, most client devices can't use 160 megahertz channels because it uses those DFS channels. So that drops your bandwidth that you can use to 80. So that drops our speed to 433 megabits per second. Now, the problem we run into, you can only use 256-bit QAM when the signal to noise ratio is really good. Your signal to noise ratio is good, but it's not really good. So now it drops us back down to 64-bit QAM. And now our maximum data rate drops to 325 megabits per second. So if you were to combine, connect with the client device at these situations, so you're connected at a 325 megabit per second data rate, and you did a speed test, your speed test would probably be 120 to 140 megabits per second, because then you have to subtract out all of the overhead that goes into that Wi-Fi connection. So that's how you figure out your speeds. So the next question we get, which is just as fun, is how many client devices can I get on my access point? This access point says it supports 1,000 clients. So I'm just going to put one of these in my expo hall. Why is it doesn't work? So the number of clients you see on a data sheet, again, doesn't matter whose data sheet it is, means nothing. Whatever that number is, it's bigger than you're going to be able to get in the real world. All that number is how much memory is allocated to be able to handle associations. Your number of clients is going to have nothing to do with the vendor or brand or what you see on the data sheet. How many clients you are able to get on that access point has to deal with what those client devices are doing and how much airtime is available. Again, everybody has to take turns transmitting, ignoring MuMIMO, which just complicates things. It doesn't remove this issue. It gives us some bendy room. But as a rule, everyone has to take turns on that channel broadcasting. There is only so much bandwidth and time that is available that everyone has to share. So for instance, I have an access point here at home. I have 60 devices connected to it, no problems. Why? Because those client devices are all smart home devices. They're all, smart plugs, smart light bulbs, things like that. They don't send or transmit much data, so they're not stepping on each other's toes. They very rarely have to send data. They very rarely have to receive data, so there's plenty of airtime to share. If those 60 devices instead were Roku smart TV plugs, you would not be able to have 60 of them on there and use them because they would all need to be receiving video streams being transmitted to them, and those video streams are taking up the available airtime. So this is all going to depend on what your clients are doing and how fast the individual clients are connected to your network. If you have a Wi-Fi 6 access point and you have a Wi-Fi 6 client that's really close to the access point, they can transmit data really fast, so they don't use a lot of the airtime. But if that was instead somebody using a tablet that's only got an 11N chip in it, and they're kind of far away from the access point, they're going to need a lot more airtime to send that same amount of data. So your slower client devices are going to reduce the number of simultaneous users you can get on the network before you start running into complaints from your users. So to try to illustrate that, I've got a real world example here. We have an access point that is broadcasting with a 20 megahertz channel. And your client devices, we're going to say, are streaming a video. This video streams at 3 megabits per second. In this scenario, we've got a laptop. Because it's a beefy laptop, it can support 3 spatial streams. So with this, you're able to fit 34 laptops on that access point. And they're all going to be able to stream that 3 megabit per second video simultaneously without issues. You end up with roughly 100 megabit per second aggregated throughput. Now, if we change the client device to a client device that only supports 2 spatial streams, we can only fit 21 of those clients on that access point before they start running into issues, because it takes more time for them to receive those packets So they're eating up more of the available airtime, and you only end up with 65 megabits per second aggregated throughput versus 100. Now, if we connect to a cheap smartphone that only supports one spatial stream, that's what your client devices are using, you can now only get 10 clients on that access point before you start running into complaints about the connection not being able to keep up, again, because they are slower and you're having to use more airtime to send the same data. And you end up in a situation with only 30 megabits per second aggregated throughput. So this is why when you call us up and say, hey, how many clients can I put on this access point? The answer is, we don't know. The access point isn't the issue. It's just the physics of, the time needed to be able to broadcast and how fast your client devices are able to do that. So obviously the specs of the client device matter, but also the distance right to the access point in the RF environment matters, because you may not be able to connect at the fastest speed available on your client device because the signal is too weak, the signal to noise ratio is too poor, etc. So now moving on a little bit, I think we're talking about smart antenna now. We're talking about co-channel interference. So co-channel interference is just that interference from other devices broadcasting on the same frequency or a bordering frequency that you're currently using. The traditional way of dealing with that is to spend a lot of time carefully planning out which channel each access point is going to use to maximize the gaps between overlaps. And then the second thing you would do is you would turn down the power on the access point to more closely match the power of your client devices, so you have less AP to AP interference due to how far that signal can go, because it's so much more powerful than your client device. Now, the trade-off with doing this is you reduce poor performance due to interference, but you get worse performance due to worse signal to noise ratio, because because most of your client devices are primarily downloading data, and the transmitted signal is going to be lower, so the overall signal to noise ratio will be worse, so you'll get lower data rates, right? Pick your poison. So the solution to this is our smart antenna technology. So these are our access points that have the letter S after the name. Ruckus has their BeamFlex Plus. It's a similar but different technology with many of the same benefits. And basically what happens here is you have an access point that, instead of having a set of antennas, has an antenna array. And this antenna array is capable of hundreds of different antenna patterns. And so we have an algorithm that optimizes the antenna pattern to focus the beam towards the Wi-Fi client it's currently communicating to, but also allows us to ignore other sources of RF interference. So we look at where other sources of RF interference are coming from and try to choose an antenna pattern that ignores it, basically allows us to not hear it. It would be like if somebody was shouting in your ear. If you put an earplug in that ear, your other ear can hear better because you've reduced that other source of interference, type of thing. So one of the cool things about smart antenna, it requires nothing special on the client device. And unlike beamforming, it works with mobile clients who are changing position and relationship to the access point. So we have a case study here that we did that helps illustrate this. So this is a hotel, and this is one of the more modern upscale hotels where every room has an access point in the room. So for our test here, we have 2 floors, one on top of the other. And we are using 5 gigahertz. So we've got a bunch of different channels here to use. So you can see our test is done on channel 100. So there's, 2, depending on how you measure it, there's 2 rooms between this access point and this access point. And there is a floor between these access points and this access point up here. So to test this, we used our old wall plate. We don't make this one anymore, but it's the same smart antenna technology that we have today. And we used a ubiquity access point with roughly the same specs, remarkably close to the same specs, but no smart antenna. So with one access point operating, multiple clients connected, the aggregated throughput was 400 megabits per second. Airtime utilization was roughly 67%. So same between both of them, same performance. Smart antenna did nothing. But when you turn on that second access point, so you've now got two access points operating on the same channel. They are physically separated from each other, but that signal can go farther than you think. There is overlap, so there is interference issues. When using smart antenna, we had an aggregated throughput of 785 megabits per second. The Ubiquiti without smart antenna, their aggregated throughput was 555 megabits per second. So how is that? Why are we getting so much better through aggregated throughput? It's because we're able with smart antenna to ignore some of that interference. And it allows us to achieve 131% airtime utilization. So basically 31% of the time there is overlap that is not causing interference. Whereas with Ubiquiti, they maxed out at 95% airtime utilization. Right, just about as good as you could theoretically get. So we add a third access point, and now you see here the aggregated throughput jumps up to 900 megabits per second on the Zycell with smart antenna. And with non-smart antenna, it's roughly the same as it was before with two access points. Another key thing to see here is with smart antenna, each access point is getting roughly the same aggregated throughput, where with the non-smart antenna, it's Wild West, and some APs are doing much better for their clients than others are. So in addition to higher aggregated throughput, it's more evenly distributed. So overall, the wireless users, no matter which access point they are connected to, are getting the better experience. Okay, so now let's talk about some of the different newer Wi-Fi technologies, because a lot of people still aren't up to date on those. So shortly after Wi-Fi 6 came out, there was the launch of Wi-Fi 6E. So what Wi-Fi 6E did is it took what was already being used for Wi-Fi 6 on 2.4 and 5 gigahertz, and it expanded it to a new chunk of spectrum that was opened up for unlicensed use called 6 gigahertz. So the benefits of 6 gigahertz are you've now got more overall bandwidth available than 2.4 and 5 gigahertz combined, making it ideal for those dense deployments where you've got a lot of access points or a lot of users, because you've now got a lot more channels available for you to use, right? So with 5 gigahertz, using 160 megahertz spectrum, you only had 2 channels that you could use. Assuming your clients could even support DFS, you only had 2 channels to choose from. So as soon as you added a third access point, you would have interference issues. With Wi-Fi with 6 gigahertz, you've got 7 non-overlapping 160 megahertz channels, right? So you can now use 160 megahertz channels in an office, in a condo, and you don't have interference issues because there's enough bandwidth available. So why aren't we all using 6 gigahertz today, right? There are some trade-offs. The first one is 6 gigahertz is higher frequency, therefore the range is less. So you probably have to not just replace your current access points, you will probably have to add a couple extras to provide the same coverage area as you were providing today with 5 gigahertz. Or you just leave some holes in your 6 gigahertz coverage and your client drops back to 5. Higher prices. You've now got 3 radios operating at the same time, in theory, up to 3 radios instead of 2. So you need to power 3 RF chips, 3 sets of amplifiers, and you need a faster, bigger central processor to handle the extra data that you're going to be sending. So that drives up prices. For faster speeds, again, you've now got 3 radios. Your existing PoE infrastructure may not support it. So you may need to also upgrade your switches to provide higher PoE output power. You may also run into the issue where your Ethernet is now your choke point on your networks. You may also want to upgrade your switches to multi-gig switches to handle the increased wireless data rates. The other problem we run into is 6 gigahertz cannot by default be used outdoors. So the problem we've run into is much like with 5 gigahertz, there are already people using 6 gigahertz that are licensed users, and they haven't gone anywhere. Now, because 6 gigahertz doesn't travel as far as 2.4 or 5, it's not an issue if you're using 6 gigahertz indoors. But outdoors, where you've got a lot of open space, your signal can travel too far. So the way that the FCC has dealt with this is not to do DFS because of all the issues with DFS. Instead, they've got a newer, improved technology. I think it's called AFC, automatic frequency something. Sorry, my mind's going blank on what the actual acronym is. Maybe I've got it on a future slide here. But basically, what happens is if you want to use 6 gigahertz outdoors, you have to buy special outdoor 6 gigahertz equipment, and that equipment has to be either super low powered or it has to use the automatic frequency selection here to choose what channels to use. So basically what happens is your outdoor access point has to connect to a third-party service. There's a bunch of these third-party services, and what they do is they keep a database of all of the licensed users, where they are physically located, what geography they're operating in, and what channels they're operating in. And every 24 hours, your access point has to check that database. And if anybody is in your area using the channels you're using, you have to either change the channel you're using or you have to reduce the bandwidth you're using to not cause any issues. So that obviously drives up the cost of access points. It now has to maintain connectivity with this third-party service. There's lots of different third-party services that provide this function. So you have to go and get certified and make sure you're compatible with each ones or create a list of compatible AFCs that you can work with. AFC, that's the acronym, automatic frequency control. And then you probably have to pay these third parties to provide that data to you, right? It costs them money to operate. So you have to then subscribe to them, whatever their business model may be, before you can use 6 gigahertz outdoors. So there are outdoor 6 gigahertz solutions. We currently do not offer any for those reasons. Eventually we will have some, but it's not like the good old days where you could just take an indoor access point, put it in a plastic housing and mount it outdoors somewhere. I mean, you could do it, but it wouldn't be legal. After 6E, very shortly after 6E, Wi-Fi 7 came out. And Wi-Fi 7 is essentially replacing 6E products. So Wi-Fi 7 gives us a number of improvements over 6 gigahertz. We can now use up to 320 megahertz channels. So with 6 gigahertz, there's still plenty of non-overlapping channels. So it makes 320 megahertz viable in a lot of environments. We've increased the QAM from 1024-bit QAM to 4096, so we can cram more data into the same bandwidth. And we've got some cool new technologies. The first one is called multi-link operation. All of our access points that are Wi-Fi 7 support this, and in fact is going to become mandatory on all new devices starting this summer. And what this does is this allows your client device to connect to multiple radios in your access point. So right now you have an access point that's probably broadcasting on 2 channels. If it's 6E or 2 radios, if it's 6E, it may have 3 radios, 2.4, 5, and 6. Your client devices will only connect to one of those radios at a time. With Wi-Fi 7 and MLO, they can now connect to multiple radios simultaneously. So they can connect to the 5 gigahertz radio and the 6 gigahertz radio at the same time and use both radios simultaneously to transmit or receive data. So that means you can aggregate your speeds so you get even faster speeds. It helps you deal with interference. So if one radio is having interference, the data can go through the other radio without needing to disassociate and reconnect. You get lower latency because there's less rebroadcasts, etc. So a huge benefit. To make it confusing, there's lots of different flavors of MLO on the client side, and many client devices will say they support MLO, but they don't really do it. For some silly reason, You can call your product MLO, or there is a flavor of MLO which only uses a single radio. But it just makes for faster switching between the two than traditionally what you would get with 6E, but they're allowed to call that MLO. So when it comes to testing MLO and verifying it, there's going to be a huge variety of support and benefit for your client devices, depending on what flavor they are supporting. The other cool thing we have is multi-RU puncturing. So one of the challenges with using these big wide channels, 320 or 160 megahertz or whatever, is the interference issue. You're using a bigger block of spectrum, you're much more likely to run into somebody else also using part of that. And if you get interference in any one part of the channel, it's interference across the whole channel as far as your clients are concerned. Multi-RU puncturing solves that. So let's say you're using a 320 megahertz channel, and it overlaps with some other source of RF that's using a 20 megahertz channel. We can create a hole in that 320 megahertz and continue to broadcast at 300 megahertz, skipping over where the interference is, so you don't deal with the interference. So it's a lower bandwidth, but it is much more predictable because it's not interference based. So that's a cool technology to have that Wi-Fi 7 gives us. Just a quick comparison of the different technologies. Let's just skip that. It's late. I've been talking too much. So the main benefits of 6 gigahertz today, and the other challenge we have with 6 gigahertz is a lot of client devices don't support it yet. It's something you mostly only find in feature phones, higher end laptops, and MLO only in the top lines of those. So 6 gigahertz, though, is going to obviously get more support as time goes on, but it's really good for high density deployments. Anywhere you've got a lot of access points in the same area or anywhere you've got a lot of users, because there's so much more bandwidth available for everybody to share, you're going to reduce those congestions issues. You've got more airtime available to use for everybody. And then anything where you need faster speeds. So if you're trying to transmit HD video, you can do that today with Wi-Fi 6, but you have to compress the video, which adds some latency. So in theory, Wi-Fi 7 gives us fast enough speeds that we can send uncompressed video or media at higher resolutions, allowing for real-time, almost no latency video streaming using Wi-Fi technologies. And then this one is about Zycel, because we get this question a lot. If you look at the data sheets, you'll say, hey, there's an NWA and there's this WBE or WAX, and it looks like they've got the same spec. So I did want to throw this in here today when you're looking at our products. The differences between the NWA series and the WBE series. So to begin with, the NWA series is split into two families. Basically, those with the number under 100 and those with the number over 100. So those with the number under 100 tend to be more of our SOHO or prosumer type access points. They only have a 2-year warranty on them, and they may be missing some features like they may not support load balancing, they may not support captive portal, etc. From the 100 series and up, those ones have lifetime warranty, and those are our true small business access points, and they generally have access to all of the features you would expect to see or that you would find in Nebula. Our W series are our Nebula Flex Pro access points. So these will come bundled with 1 year of Pro Pack, which is an optional license for our cloud management platform. But these are also the access points that support a local controller. So if you don't want to use cloud for management, but you do want a controller, W series works with our local controller. The W series also supports collaborative detection and response, where your firewall gateway and your access point talk to each other and coordinate with each other on certain types of threats. The W series supports our secure Wi-Fi, where you can convert the access point into a remote VPN appliance. And the W series is where you generally find our advanced antenna technologies, dual optimized antenna, smart antenna, etc. So those are what the differences are. Okay. So another technology to talk about here, this is a Zycel technology. As far as I know, we are the only ones using it, is what's called dual optimized antenna, right? So your traditional access point has a antenna pattern that's optimized based on the idea that you're mounting your access point on the ceiling in the air directly over the area to be covered. And unfortunately, in the real world, at times you do have to do wall mounting instead. And what happens is you end up sending a lot of the signal into the ceiling, into the floor. You don't get the horizontal coverage that you would ideally want to have. And you may be causing interference depending on what's above and below you. So our solution to this is something called dual optimized antenna. For those of you that need something more advanced than your traditional fixed antenna, but don't want to spend the money for smart antenna, we have this dual optimized antennas. And what that does is it lets the access point itself has two sets of antennas. One that's optimized for ceiling, one that's optimized for wall mount. And you can go in and tell it which to use based on where you've installed that access point. Okay, so some general mounting tips. Again, most access points are optimized for being mounted above the area to be covered rather centrally. So that's what you want to do. You want to mount the access point as high as possible within reason over the area to be covered. You know what you're trying to place it is at a height where the signal can travel from the client to the access point while traveling through the minimum number of obstructions and while minimizing the distance between the two, right? You don't want to necessarily, if you've got a ridiculously high ceiling, you don't want to mount it 40 feet up. It's probably too high, but you do want to, optimize it so it's as close as you can be while also minimizing the obstructions, such as in this case, the cubicle walls. You don't want the signal going through the cubicle wall because those have metal and dense wood in them. They degrade the signal. So if you are mounting this, we're in a traditional office environment where you have a drop ceiling. If your local building codes will allow it, instead of poking holes in the drop ceiling and funneling cables through it, just mount the access point above the drop ceiling where you can just rest it there. Drop ceilings are generally made out of some thin, porous cardboard-like material that don't have much attenuation. They don't affect the RF signal that much. So you can just simply rest them on the drop ceiling itself, and then people can't see the access point. There's no holes, there's no cables. It's a cleaner install. But again, your RF environment or your building codes have to allow you to do that. And in many places, you cannot legally do that. Paul had a question saying, what's the optimum height? And I don't think there is one in general. I would say probably no more than 20 feet above the area to be covered, but it depends what's there. If it's a wide open area, you may be able to drop it a little bit lower, maybe more ideal. If there's, extra tall cubicle walls, you may want to mount it a little bit higher. You're just trying to get the, balance distance versus being able to avoid any obstructions that might absorb or block the signal. And then when you are mounting up there above the drop ceiling, keep in mind all the ductwork, lighting, things like that are generally metal, and metal and radio waves do not go together. So you may need to, if you don't have a drop ceiling, for instance, you may need to use some what do you want to call them? I want to call them extenders, but that's not the right term. But basically, they're poles. You mount the pole to the ceiling. The end of the pole has a flat piece of metal that you can then screw your access point onto, dropping them below these other sources of RF interference or signal blockage. When it comes to hotels, the traditional way of doing things for 20 of the last 25 years is what we call umbrella coverage. And you still see that today with lower end hotels where the owners are really cheap. And basically that means you mount the access point in a hallway, and that one access point covers 4 rooms, 6 rooms, 8 rooms. I've even seen some of the cheaper guys out there try to cover up to 16 rooms with a single access point. And it used to work okay back in the days where most people didn't have Wi-Fi, where most phones weren't smartphones, or if they were smartphones, you were just checking your email. That type of coverage doesn't work in today's modern RF environment where everybody's got one or more devices and they're probably going to be streaming video or doing other things that use up a lot of airtime. So you end up with too many users on one access point. The other challenge you run into is in a lot of hotel designs, if you're mounting out in the hallway, what's the closest room in the hotel room itself, it's the bathroom. And the bathroom's got thick, dense tile walls. It probably has a bunch of pipes and conduits in those walls that block the signal. So most modern hotels are doing one access point per room or one access point for every other room. Every major vendor of access points sells specialty access points that are designed specifically to mount in the room. They're generally lower power to help prevent bleed over because you've got so many access points. And they usually have Ethernet pass through. So you can run one Cat6 cable to the room. It powers your access point, and then you've got Ethernet out to the IPTV and to the IP phone in the room. So you're just running one Cat6 cable to the room instead of having to run two wire in addition and stuff like that. In general, look for access points where you can turn off the LEDs. Nobody wants a flashing LED on the ceiling when they're trying to sleep and they're jet lagged. And in general, you want a mount that locks, or at least isn't obvious how to release it. Because if you mount this access point where people will see it, can see it, people will steal it. You want to deal with public areas much differently than how you deal with their individual rooms. And when you do that, basically you want to divvy up the other areas in the hotel and plan for each of them independently. So do the lobby area separate from the bar, separate from the conference room, separate from the expo center. Plan those out. And in generally in these wide areas that are largely wide open, you want to plan based on the number of clients you have rather than square footage. Generally, the more clients that will be in that area and connected to Wi-Fi, the more APs you're going to need. So a hotel bar probably doesn't need very many access points because while you may have a lot of people in there, they're probably not, watching Netflix. Um, but in an area where you have a conference room where you've got a lot of users crammed in there who probably are going to be, either working at the same time they're watching whatever the seminar is, or are bored and just looking for amusement while they're sitting there half listening, you'll probably need more access points. And one thing just to highlight here, we have run into this before. When you were setting up your load balancing, you want to, again, break that up based on the physical area where those users are. We have had people that have tried to turn the entire hotel into one load balancing situation, and you run into issues where the load balancer doesn't know that one AP is in the lobby and the other AP is on the fourth floor. So it's trying to load balance people to an AP, which can't reach those users. So you divide up your and create load balancing groups based on the physical location. When it comes to schools, it's really variable based on the type of school and the type of classrooms. So there are classrooms out there where the kids, only are using the Wi-Fi for doing tests, for submitting homework assignments, for things like that. There are other types of smart classrooms where the teacher, instead of broadcasting a PowerPoint or a video onto a front wall, instead streams the content to each kid's unique individual Chromebook or iPad. So obviously that makes a big difference based on the use situation with how many access points you need. It is very common to need two access points in a single classroom if it's a classroom with a large number of users and they are doing video streaming or screen mirroring in that room. And in general, if you have more than 30 students in the room, use smart antenna. You will benefit from it. And with that, guys, we are done. If there are any questions, send them in. Again, you can send them in using chat or using the Q&A, and I will stick around for a minute to answer some of those for you. This was recorded, and this should show up on our YouTube channel probably by tomorrow afternoon. So Thomas has a question here. I have two access points standing directly under them, one at a time. I assume you turn one off and turn the other one on. AP1 gets 350 megabits download. AP2 gets only 50 megabits download. I can't figure out why. Assuming the access points are the same model and assuming they're connected together or configured the same and both are not on at the same time, I do not know what would cause that. other than one maybe on a different channel than the other, and that channel may have some issues. So you may need to manually go in and set them both for your test to the same channel. But if they're different models, there could be all sorts of issues there, um, in terms of, maybe the MLO, they don't support the same number of spatial streams, or there may be a chipset compatibility issue between the chipset being used in the client and the chipset being used in the access point. It's hard to know without, a little bit more details. So 660, yeah, different channels. So it's probably a channel issue then. Um, but that would be something that you would probably want to call in to our tech support or talk to your sales guy and get our sales engineer involved so they can look more detailed into it to see what's going on. There are some types of logs that only our headquarters can pull up if you're using Nebula. So they might be able to look at it and see what else is going on there. But if there are different channels, that would be my first guess, is that there's some sort of interference on that second channel. So that would be a test, is to swap the channels between the two access points and see if the performance also swaps at the same time. That's all I can think of off the top of my head now, but definitely tech support, or probably better our sales engineer, because the tech support guys are pretty busy. Could help try to narrow and troubleshoot what's causing the issue. And that looks like that's it for questions. So I'm going to go ahead and end today's webinar. Thank you for sticking around for all of this. I know it ran an awful long time. Hopefully I see you at one of our future webinars. Thank you.